Okay, so today's part 2 of the Bioinformatics Project series, where we will show you how to apply data science for drug discovery. And in the previous video, I've covered about how you can collect data directly from the bioactivity database, CHEMBO. And so in today's video, we're going to take a step further by computing molecular descriptors, and we're going to then perform exploratory data analysis on the computed descriptors. And so without further ado, let's get started. Okay, so the first thing that you want to do is head over to the GitHub of the dataprofessor, and you want to click on the code repository, and then scroll down and find Python. And so before we proceed with doing part 2, exploratory data analysis, we're going to do a recap of part 1. And we're not going to do an ordinary recap, but we're going to do a concise version. And so in this concise version, let's have a look. We've trimmed down the code and it will be a bit more lightweight. Okay, so I'll show you that in a moment. And so what you want to do now is you want to scroll down and right click on the raw link and then save link as, and then you want to save it into your computer. Okay, and then you can follow along on your local computer using Jupyter Notebook. However, if you want to use Google Colab, we can do that as well. And so let's go to the Colab right now. And so in Colab, you can click on the File, Open Notebook, and then click on the GitHub tab. And then you want to type in dataprofessor. And then go to the code repository. So make sure that it is dataprofessor/code. And then you want to click on the CDD-ML part 1, bioactivity data concised. Okay, but I'm going to use the one already in my Colab. And aside from part 1, we're going to also do part 2, which is also in the Python repository under code. And then you want to click on the CDD-ML part 2, exploratory data analysis. And then you want to right click on the raw link and save link as, and then also save it into your computer. And so we could do the same thing right inside Colab by File, Open Notebook. Okay, and then you want to click on the GitHub and type in dataprofessor/code, enter. And then you want to find CDD-ML part 2, exploratory data analysis, and click on that one. Okay, but since I already have it locally, I'm going to use it. Okay, so let's start with part 1. So you want to click on the connect, and then give it some time to load up. Okay, so let's go over what I have done in this concise version. So essentially there's two things. So the first thing is that redundant code cells were deleted. And the second part is that code cells for saving files to Google Drive has also been deleted. And so at the end of the notebook, we can simply download it by clicking on the Files button on the left-hand side of the panel, and then we could download a copy of the zip file of the curated data. Okay, so I'm going to show you that in just a moment. All right, so the notebook is loaded, and you want to install the CHEMBO web resource client. So go ahead and run the cell. All right, so it's installed. And let's go ahead and import the libraries. And let's run the code cell for searching for coronavirus. And this is the result. And so we're going to select the 5th entry, which has the index number of 4 right here. And so let's run that code cell. So a detailed explanation of all of this has already been given in the previous video. So I'm just going to run the code cell one by one. So if you want further information, please check out the previous video of part 1. Okay, and so this is the bioactivity class label. Combine the data frames and writing out the output file. Okay, and so let's download the preprocessed file. And there you go. right? So a recap, in order to download this file, make sure that you hover your mouse over the 3 dotted line on the far right of the name of the file, and then click on it and then choose download. All right, so we're done with the part 1, and so now let's continue with part 2. And so it should be noted that explanation for all of the code cells in this part 1 has already been given in the previous video, the part 1 of the Bioinformatics Project series. Okay, and so let's proceed to the contents that are intended for this part 2 of the Bioinformatics Project series. And so let's close this notebook, and now let's go to the part 2 and make sure to click on the connect, and then you want to run the code cell for installing Conda and RDkit. And so what RDkit essentially will allow you to do is it will allow you to compute the molecular descriptors for the compounds in the dataset that we have compiled from part 1. Okay, so let me explain again. In part 1, we have already downloaded the dataset of the biological activity from the Chambo database. And so the dataset will comprise of the molecule names and the corresponding SMILES notation, which is the information about the chemical structure, which we will use in this part 2 in order to compute the molecular descriptors. And the data from part 1 also contains the IC50, which in part 1 we have already performed the binning into the bioactivity class: active, inactive, and intermediate. Okay, and so in this part 2, we're going to select only 2 bioactivity class, which are the active and the inactive, so that we can easily compare between the active compounds and the inactive compounds. Okay, and so without further ado, let's have a look at the code. So now Conda and RDkit has already been installed. And so let's load up the pandas library, and make sure to click on the file button here on the left hand panel, and then you want to upload and then choose the bioactivity data that we have prepared from the previous part 1. Okay, and so it's right here now. It has already been uploaded. And then we can close the panel here. Okay, and so let's load up the CSV file. So the following block of codes, we're going to compute the Lipinski rule of 5 descriptors, or simply Lipinski descriptors. You might be wondering, what is Lipinski descriptors? Well, Lipinski descriptor originates from the fact that Christopher Lipinski, who is a scientist at Pfizer, came up with a set of rules called the Rule of 5, which was used to evaluate the drug likeness of compounds. And so the drug likeness is based on the key pharmacokinetic properties comprising of absorption, distribution, metabolism, excretion, which has an acronym of ATME. And this is also known as the pharmacokinetic profiles. And so what essentially ATME will tell us is that it will tell us the relative drug likeness of the compound, whether it can be absorbed into the body, distributed to the proper tissue and organs, and become metabolized and eventually become excreted from the body. And so in order to derive the rule of 5, Christopher Lipinski collected a set of FDA approved drugs that are normally administered orally, and then based on his analysis, he observed that the 4 descriptors that was used for his analysis had corresponding values in multiples of 5 as follows. So the molecular weight should be less than 500 Dalton. The octanol water partition coefficient, or LogP, has to be less than 5. Hydrogen bond donors is less than 5. Hydrogen bond acceptors is less than 10. And so as you can see, all of the values are multiples of 5. Okay, and so let's proceed with computing the descriptors. So let's load up the library and then compute the descriptors. So this is a custom function that was inspired from this link here, and it was modified to include the descriptors for this analysis. All right, and so we have the Lipinski descriptors in this data frame, and in order to get that, we're going to apply the custom function called Lipinski, which was the custom function here, which takes in as input the SMILES notation. So the SMILES notation contains the chemical information. And so what the chemical information tells us is the exact atomic details of the molecule. And so it's going to use that as the input to compute the molecular descriptors. All right, and so let's continue. And so let's run that. And let's have a look at the data frame. All right, so we can see that there are 4 descriptors that we have previously covered, including molecular weight, LogP, which will tell us the size. LogP will tell us the solubility. And so this is the relative number of the hydrogen bond donors and acceptors. And so we can see that there are a total of 133 rows and 4 columns. And as a recall, the data frame that we have read directly from the curated file from part 1 is shown in the DF data frame. And so we're going to combine the DF data frame and the Lipinski data frame together because we want to have the standard value and the bioactivity class columns. And so we're going to use the pdconcat function in order to combine the DF and DF Lipinski data frame. And then we're going to put it into the DF combined variable. And then let's have a look at the new data frame. All right. And so you can see that the last 4 columns are integrated into the DF data frame here. All right, and so the dimensions of the data frame is correct, 133 rows, and then the number of columns has been expanded to be 8. Okay, and so now we're going to convert the standard value, which is the IC50, to the PIC50 scale. And so the reason for doing the IC50 to PIC50 transformation, which is essentially the negative logarithmic transformation from the IC50 value, is that the original IC50 value has uneven distribution of the data points. And so in order to make the distribution more even, we will have to apply negative logarithmic transformation. Okay, and so let me give you a challenge. Let me know how the distribution of the original IC50 looks like versus the PIC50 that you have performed the transformation. So let me know in the comments after you have tried this. And so a hint is that what you can do is perform a simple scatter plot. Okay, and so let me know in the comments if you see any difference in the distribution of IC50 versus the PIC50. Okay, so let's do the actual transformation by running this custom function. Oh, and one point here, which is worthy to note, is the IC50 value, which is contained inside the standard value column, has large numbers, and the large number here will, after performing negative logarithm, it will become a negative value. And in order to prevent that, we're going to need to cap the maximum value right here to be here 100 million. So we need to cap the value to be 100 million so that the resulting PIC50 would not be less than 1.0. Otherwise, it will have negative values and that will make interpretation a bit more difficult. Okay, and so we're going to cap the values to 100 million by creating a custom function called norm value. And so what essentially the norm value function would do is that it will read through the individual values in the standard value column, and if the value is greater than 100 million, it will cap the value to be 100 million so that the value will not exceed 100 million, and so therefore after performing negative logarithmic transformation, it will not be less than 1.0. Okay, and so let's perform the norm value here. Let's describe the value again. And notice that the maximum value is 1 times 10 to the 8th power, so it is 100 million. Whereas previously, the value is rather big. Okay. Okay, and so we're gonna apply the PIC50 function to the normalized data frame, and then we're gonna call the new data frame to be DF final. Okay, and so notice that we have now created a new column called PIC50, and we have already deleted the original IC50 column. Notice that the standard value here column has now been deleted and it is converted to be PIC50, which is the negative logarithmic form of the IC50. And so let's describe the data frame. All right, and so now the maximum value is 7.3 and the minimum value is 1.0. And what we want to do now is to allow simple comparison between the 2 bioactivity classes. Therefore, we're going to delete the intermediate class, and we're going to call the new data frame to be DF2 class. All right, and so we have now 119 rows by 8 columns. And so let's perform exploratory data analysis using the Lipinski descriptors. And so in cheminformatics or drug discovery, we're going to call the exploratory data analysis to be chemical space analysis, because what it essentially does is it allows us to look at the chemical space. And the chemical space is kind of like a chemical universe, right? So as Jose Medina Franco puts it, each chemical compound could be thought of as like stars. Okay, and so the active molecules would be compared to a constellation, and it will be referred to as constellation. And so he developed a approach which he termed constellation plot, whereby you could perform chemical space analysis and create the constellation plot, whereby the active molecule would be correspondingly have larger size in comparison with the less active molecule. And so we're going to apply a similar concept in our plot here, as I will show you in the next few moments here. And so what we want to do first is import the library, Seaborn, and the matplotlib as PLT. And so now we're going to create a simple frequency plot of the two bioactivity classes. So using this block of code, we're going to create a frequency plot comparing the inactive and the active molecules. And in doing so, we're also going to save it as a PDF file, right? And so the X and Y labels are obtained using these two lines of code, and the frequency plot is using the count plot function, where we use X variable to be bioactivity class right here. And so as you can see, there's no need to define the Y variable, because the Y variable here is the frequency. And so the edge color is black, which means that the bar will have a black outline. Okay, and so being able to save it as the PDF file will allow you to use the resulting files for your report, for your publication, for your project. And as I have already mentioned in the part 1 of this Bioinformatics Project series, these two notebooks are crafted based on actual research protocol that we use in our own research group. Okay, and so let's proceed. All right, so now we're going to make a scatter plot of the molecular weight versus the LogP, or the solubility of the molecules. And we're first going to start by defining the figure size to be 5.5 by 5.5. And we're going to use the scatter plot function here, whereby the X variable will be MW, or molecular weight, and the Y variable will be the LogP, and the data will be df2 class. And the hue here would refer to the color, and so the color will be defined on the basis of the bioactivity class. And because there are two classes, you will see that the color comprises of blue and orange, whereby blue will refer to the inactive molecule and orange will refer to the active molecule. And the size of the data points here will be according to the PIC50 values. And we define the edge color to be black, which is the edge of the circles, and the alpha transparency is defined to be 0.7. And the X label and Y label are custom here, MW and LogP, with a font size of 14, and we have the font weight to be bold. And in this line, we're going to define that we want the figure legend to be outside the plot. Otherwise, it will be embedded inside, which will make it very difficult to see. So we opted to have the figure legend outside. And then finally, we're going to save it into the PDF file. Okay, so let's run this block of code here. All right, so it's finished. And so let's do the same thing for the PSC50 value. So the same concept applies, just changing the name of the variables. And so here we see the distribution of the inactive class and the active class. And so this is to be expected because we use the threshold to define active and inactive. And so the threshold that we used was 5 and 6, right? So if the PSC50 value is greater than 6, it will be active. And if the PSC50 value is less than 5, it will be inactive. And so you can see that the distribution of the inactive is rather vast in comparison to the distribution of the active molecules, which is between 6 and 7, whereas the inactive is between 1 and 5. Okay, and so we're going to perform Mann-Whitney U-test in order to look at the difference between the two bioactivity class, active and inactive. And so we're going to apply this Mann-Whitney U-test to test the statistical significance of the difference, whether they are different or not different. And so the code for performing the Mann-Whitney U-test was modified from machinelearningmastery.com, and we made it into a function. All right, and so let's run it. And let's apply the man-Whitney function to the PIC50. And what it will do is it's going to compare the active class and the inactive class to see whether there is a statistical significance for the PIC50 variable. And so based on this analysis, the p-value is rather low, and therefore we reject the null hypothesis. And therefore we can say that it is having different distribution, meaning that active and inactive. Okay, and so we're going to apply the same plots and statistical analysis for the other 4 Lipinski descriptors as well. And so let's breeze through this. Box plot, man-Whitney, box plot, man-Whitney, box plot, man-Whitney. Oh, again, okay. Man-Whitney, box plot, man-Whitney. And so make a note that all of the files from the man-Whitney and the box plot are saved as files. And so the man-Whitney has its own CSV file and the box plot has its own PDF file. And so we can download all of this at the end in order to use it for your own project and research. And so let's have a look. But before we do that, let's do some interpretation of the results. Okay, so let's make sense of the results here. So let's start with the PIC50 values. So taking a look at the PIC50 values, the actives and inactive displayed statistically significant difference, which is to be expected because the threshold value was already defined at 6 and 5, okay, as I have already explained. Of the 4 Lipinski descriptors, only LogP exhibited no difference between the active and the inactive, while the other 3 descriptors comprising of MW, number of hydrogen bond donor, and acceptor, shows statistically significant difference between the active and inactive. Okay, so let's continue. Alright, and so finally, we're going to zip up all of the files comprising of the CSV files and PDF files, which was generated in this notebook. And so all of the man-Whitney U-test and the box plot will now be zipped up, and we can conveniently download it into our computer. So let's zip up the file and click on the File button on the left panel. And then hover your mouse on the 3 dotted lines, click on it, and click on download. Alright, and so it will download into your computer. And so you will see the plots that we have generated in the notebook and the resulting man-Whitney U-test. Okay, all of them are downloaded as CSV file. Alright, so if you find value in this video, please give it a thumbs up. And if you haven't yet subscribed, please subscribe to the channel. And as always, the best way to learn data science is to do data science. And please enjoy the journey. Thank you for watching. Please like, subscribe, and share. And I'll see you in the next one. But in the meantime, please check out these videos.